So here's something to think about as you're lying there, settling in for the night. Right now, in this very moment, something extraordinary is happening inside your skull. About 3 pounds of wet, wrinkled tissue, roughly the consistency of soft tofu, if you can believe that, is generating the entire world you experience. Every color you've ever seen, every song you've ever loved, the feeling of a warm blanket against your skin, the taste of your favorite meal, the ache of missing someone, the quiet satisfaction of solving a problem. All of it, every last flicker of experience, is somehow being conjured by a lump of biological matter that runs on about 20 watts of power. That's less than the light bulb in your refrigerator, and yet here you are, aware, conscious, experiencing what it's like to be you. And nobody, not the smartest neuroscientist alive, not the most brilliant philosopher, not the most powerful artificial intelligence we've built so far, nobody can fully explain how that happens. How matter becomes experience, how the physical becomes the felt. It's arguably the deepest unsolved problem in all of science, and tonight, we're going to wander through it together. We're going to trace how human beings have tried to understand consciousness, from the very first people who wondered about the nature of the mind thousands of years ago, all the way to the cutting-edge theories and experiments happening right now in labs around the world. And we'll do it slowly, because this is the kind of thing that deserves to be savored, not rushed. Let's start way, way back, because people have been puzzling over consciousness for as long as we have any record of people puzzling over anything at all. The ancient Egyptians, interestingly, didn't think the brain was particularly important. When they mummified their dead, preparing them for the afterlife, they carefully preserved the heart, the liver, the lungs. But the brain? They pulled it out through the nose with a hook and threw it away. To them, the heart was the seat of the mind, the soul, the self. The brain was just stuffing. It's a remarkable thing to consider. One of the most sophisticated civilizations of the ancient world, the people who built the pyramids and developed advanced mathematics and astronomy, and they had the organ of consciousness literally in their hands and discarded it as irrelevant. The ancient Greeks, though, started to get closer. And this is where the story really begins to get interesting, because the Greeks didn't agree with each other at all. And that disagreement, that tension between different ways of thinking about the mind, is still with us today. It's still shaping the science of consciousness in the 21st century. Aristotle, for instance, sided with the Egyptians in a way. He thought the heart was the center of sensation and thought. The brain, he figured, was basically a radiator, a cooling system for the blood. Which sounds absurd now, but think about it from his perspective. The heart is warm, it beats faster when you're excited or afraid. It seems to respond to your emotions in real time. The brain just sits there, cool and inert, doing nothing obvious. His reasoning wasn't crazy, it was just wrong. But then there was Hippocrates, the father of medicine, who lived a generation or so before Aristotle, and Hippocrates got it right. Around 400 BCE, he wrote something remarkable. He said, and I'm paraphrasing here, that people ought to know that from the brain, and from the brain alone, arise our pleasures, joys, laughter, and jests, as well as our sorrows, pains, griefs, and tears. He was emphatic about it. He'd seen what happened to people with head injuries, how a blow to one part of the skull could rob someone of speech, while damage to another area might paralyze half the body. He connected those observations to a radical claim. The brain is the organ of the mind. Everything you think, everything you feel, everything you are, it comes from that organ inside your head. Now here's the thing. Hippocrates was right about where consciousness lives, but he couldn't begin to explain how it works. And that gap between knowing that the brain produces consciousness and understanding how it does so, that gap has haunted us for 2,500 years. We're still standing in it. The person who really crystallized the problem, though, the one who framed it in a way that we're still wrestling with, came much later. René Descartes, the French philosopher and mathematician writing in the 1630s and 1640s. You probably know his famous line, "I think, therefore I am. Cogito ergo sum." But what's really important about Descartes isn't that one catchy phrase. It's the entire framework he built around it, a framework called dualism. Descartes looked at the world and saw two fundamentally different kinds of stuff. There was physical matter, res extensa, he called it, the extended stuff, the stuff that takes up space, rocks, water, bodies, brains. And then there was mind, res cogitans, the thinking stuff, thoughts, feelings, experiences, consciousness itself. And Descartes argued that these were genuinely different substances. The mind wasn't made of matter. It was something else entirely, something non-physical that somehow interacted with the physical body. And you can see why this was appealing. Think about your own experience for a second. Your thoughts don't feel like they have weight or color or location. When you imagine a sunset, there's no actual light being produced inside your skull. When you feel sadness, you can't point to a specific cubic centimeter of brain tissue and say, that's where the sadness is. Consciousness feels like it's made of different stuff than the physical world. Descartes was, in a sense, just taking that intuition seriously and building a philosophy around it. But dualism has a devastating problem, and people spotted it almost immediately. Descartes' contemporary, Princess Elizabeth of Bohemia, and she's a fascinating figure, by the way, a brilliant woman who carried on an extensive philosophical correspondence with Descartes. Elizabeth asked him a question that he never satisfactorily answered. If the mind is truly non-physical, she said, how does it interact with the physical body? When you decide to raise your arm, how does a non-physical thought cause a physical movement? How does the immaterial push the material around? Because everything we know about physics says that physical effects need physical causes. You can't move a rock with a wish. So how does the ghost drive the machine? Descartes tried to answer this. He suggested that the interaction happened in the pineal gland, a tiny structure deep in the center of the brain. He chose it partly because it was one of the few brain structures that wasn't duplicated on both sides. There's only one pineal gland, and Descartes figured that since we have a unified consciousness, a single experience, the point of interaction must be a singular structure. It was clever reasoning, but it didn't actually solve the problem. It just moved it. Okay, the interaction happens in the pineal gland. But how? How does non-physical mind stuff push physical pineal gland molecules around? You're still stuck. This is sometimes called the interaction problem, and it's never been solved within a dualist framework. Not by Descartes, not by anyone since. And that's a big part of why most scientists and philosophers today have moved away from dualism towards some form of physicalism, the view that consciousness is, somehow, a product of physical processes in the brain, that there's only one kind of stuff in the universe, physical stuff, and consciousness emerges from it. But, and this is crucial, moving to physicalism doesn't make the problem go away. It just changes the shape of the problem. Instead of asking, how does non-physical mind interact with physical brain? You're asking, how does physical brain generate non-physical seeming experience? And honestly, that question might be just as hard. The philosopher David Chalmers, in 1995, gave this problem a name that stuck. He called it the hard problem of consciousness. And the way he framed it is beautifully clear. He said, look, there are lots of problems about consciousness that are hard in the ordinary scientific sense. They're complicated. They'll take a lot of work, but we can see in principle how to solve them. How does the brain integrate information from different senses? How does attention work? How do we distinguish between being awake and being asleep? These are what Chalmers called the easy problems. Not easy in the sense that they're simple. Some of them are incredibly complex, but easy in the sense that they're the kind of problems that neuroscience is equipped to handle. You study the brain, you find the mechanisms, you map the circuits, and eventually you figure it out. But then there's the hard problem. Why is there subjective experience at all? Why does it feel like something to see the color red, rather than just being an information processing event that happens in the dark with no inner experience attached? You could, in principle, build a robot that responds to red light exactly the way you do. It stops at red traffic lights, it picks ripe tomatoes, it can tell you that fire trucks are red. But would it experience redness? Would there be something it's like to be that robot, seeing red? Or would it just be processing wavelengths of light with nobody home? That's the hard problem. And what makes it so maddening is that it's not clear that any amount of neuroscience, no matter how detailed, can solve it. You can map every neuron, trace every connection, measure every electrical signal, and you'd have a complete physical description of the brain. But where in that description is the redness of red? Where's the feeling of warmth, the ache of loneliness, the taste of coffee? It seems like there's an explanatory gap between the objective facts about the brain and the subjective facts about experience. Now, not everyone agrees that the hard problem is a real problem. Some very smart people think it's a kind of illusion, a confusion generated by the way we think about thinking. Daniel Dennett, the philosopher and cognitive scientist who passed away in 2024, spent decades arguing that consciousness isn't as mysterious as it seems, that when you fully explain all the easy problems, all the mechanisms, all the information processing, all the behavioral responses, you've explained consciousness. There's nothing left over. The feeling that there must be something more, Dennett argued, is itself something that needs to be explained, not indulged. He compared it to the old idea of elan vital, the mysterious life force that people once thought must exist to explain why living things are alive. We now know there's no life force. Life is just what happens when chemistry gets complicated enough. Maybe consciousness is the same kind of thing, and that's a respectable position. But many researchers find it unsatisfying because it seems to dismiss the very thing that needs explaining. As the philosopher John Searle once put it, where consciousness is concerned, the appearance is the reality. If it seems to you like there's something it's like to taste chocolate, then there is something it's like to taste chocolate. You can't explain away the experience by saying it's not really there, because the experience is the one thing you're most certain of. So this is the landscape we're working with. This is the terrain that scientists and philosophers have been trying to navigate. And and it stretches all the way back to those ancient Greek arguments about whether the mind lives in the heart or the brain. The questions have gotten sharper, the tools have gotten better, but the core mystery, how does matter become mind, remains stubbornly, beautifully open. And the fascinating thing is that, for most of the history of science, consciousness wasn't even considered a legitimate topic of study. It was too subjective, too slippery, too philosophical. Serious scientists didn't touch it. That began to change in the 1800s, when a new discipline started to take shape. One that would try to measure the mind with the same rigor that physicists measured the motion of planets. It was called psychology, and its founders were about to discover that consciousness, slippery as it is, leaves fingerprints everywhere if you know how to look. One of those founders was a man named Wilhelm Wundt, working in a small laboratory in Leipzig, Germany, in 1879, and what he was attempting to do there was nothing short of radical. He wanted to turn inward experience into data. Think about how audacious that is. The whole tradition of natural science up to that point had been about measuring things outside of you. The arc of a cannonball, the boiling point of water, the distance between stars. Wundt said no. We can measure what's inside too. We can measure how quickly a person notices a flash of light. We can measure how two sensations feel different from each other. We can time the gap between a stimulus hitting your senses and the moment you become aware of it. He called his approach experimental psychology, and the key method he used was something called introspection, but not the casual sitting in an armchair kind. This was trained, disciplined introspection. Wundt would bring subjects into his laboratory, expose them to carefully controlled stimuli, a specific tone, a particular color, a measured weight placed in their hand, and then ask them to report, in precise and structured terms, exactly what they experienced. Not what they thought about the experience, not their interpretation, but the raw qualities of the sensation itself. Was the tone bright or dull? Did the color feel warm? Was the weight surprising or expected? He believed that consciousness, like a chemical compound, could be broken down into basic elements, simple sensations, feelings, images, and that if you cataloged enough of those elements and mapped how they combined, you'd eventually have a periodic table of the mind. And for a while, this seemed like it might work. Wundt trained dozens of students, many of whom went on to establish psychology laboratories across Europe and the United States. His student, Edward Titchener, brought the method to Cornell University and refined it into what he called structuralism, the idea that the structure of consciousness could be fully described by identifying its component parts. Titchener was meticulous, almost obsessively so. He compiled enormous lists of elementary sensations. He claimed there were over 40,000 identifiable visual qualities alone. The ambition was staggering. But here's the thing. The whole enterprise had a fatal flaw, and it didn't take long for people to notice. The problem was that introspection, no matter how carefully trained, is private. When two observers in Wundt's lab disagreed about the quality of a sensation, one said a tone felt bright, and the other said it felt sharp. There was no way to settle the dispute. You couldn't open up their heads and check. You couldn't point to a meter reading. The data was inherently subjective, and that meant it couldn't be independently verified, which is the bedrock of scientific method. Different laboratories started getting different results, and there was no objective way to determine who was right. The whole field began to fracture along the lines of who trained you and what introspective vocabulary you'd been taught. And this is where one of the most dramatic turns in the history of consciousness science happens. Because the frustration with introspection didn't lead scientists to find better ways to study inner experience. Instead, it led them to abandon inner experience altogether. In 1913, an American psychologist named John B. Watson published a paper that essentially declared war on consciousness as a scientific concept. Watson argued that psychology should concern itself only with behavior, with what organisms do, not with what they feel. You can observe behavior, you can measure it, you can replicate experiments about it. But consciousness? That's a ghost. That's philosophy. Get it out of the laboratory. Watson's manifesto launched what became known as behaviorism, and it dominated American psychology for roughly half a century. Think about that. 50 years where the official position of mainstream psychology was that consciousness wasn't worth studying. The most prominent behaviorist after Watson was B.F. Skinner, working at Harvard, and Skinner took the position even further. He argued that mental states, thoughts, feelings, desires, all of it, were either irrelevant or didn't exist in any meaningful scientific sense. What mattered was the relationship between stimuli and responses. You press a lever, you get a food pellet. That's psychology. Everything else is storytelling. Now, behaviorism wasn't stupid. Let's be fair to it. It produced genuinely useful science. Skinner's work on reinforcement schedules, for instance, the patterns by which rewards shape behavior, that's real, that's replicable, and it explains an enormous amount about how animals and humans learn. If you've ever wondered why slot machines are so addictive, or why social media feeds are designed the way they are, you're looking at applied Skinnerian psychology. Variable ratio reinforcement, rewarding behavior on an unpredictable schedule, is the most powerful way to maintain it. Skinner figured that out with pigeons in boxes, and it turns out it works on humans too. So behaviorism gave us real tools, but it also left an enormous hole. Because by refusing to talk about what's happening inside the mind, behaviorism couldn't explain some of the most interesting things that minds do. It couldn't explain why you can understand a sentence you've never heard before. It couldn't explain how a child learns language so quickly with so little explicit instruction. It couldn't explain planning, imagination, or the simple fact that you can close your eyes right now and picture a beach you've never visited. These are all things that require some kind of internal representation, some model of the world that exists inside your head, and behaviorism had no vocabulary for that. The cracks started showing in the 1950s. A linguist named Noam Chomsky, then a young professor at MIT, published a devastating review of Skinner's book on language in 1959. Chomsky argued that language couldn't possibly be explained by stimulus and response alone. Children don't just repeat sentences they've heard. They generate entirely new ones, following rules they were never explicitly taught. There must be something happening inside the mind, some kind of computational structure, that makes this possible. Chomsky's review is often cited as one of the opening shots of what became the cognitive revolution, the movement that brought the mind back into psychology. And here's what's really interesting about the cognitive revolution. It didn't bring consciousness back, not directly. What it brought back was the idea that internal mental processes are real and worth studying. Things like memory, attention, perception, reasoning, language. But the cognitive scientists of the 1960s and 70s mostly studied these processes without worrying about whether they were conscious. They treated the mind like a computer. Information comes in, gets processed, decisions come out. The question of what it feels like to process that information, the subjective experience of it, that was still considered too hard, too fuzzy, too philosophical. The cognitive revolution opened the door partway, but consciousness itself was still standing outside in the cold. So who finally let it in? Well, it happened gradually, but there are a few key moments. One of them involves a neurologist named Benjamin Libet, working at the University of California, San Francisco, in the early 1980s. Libet designed an experiment that's become one of the most famous and most argued about in all of neuroscience. Here's what he did. He asked subjects to sit in front of a clock with a sweeping hand and to flex their wrist whenever they felt like it. Simple, right? But he also asked them to note the exact position of the clock hand at the moment they first felt the urge to move, the moment they became consciously aware of their intention. Meanwhile, he was monitoring their brain activity with electrodes on their scalp. What Libet found was startling. The brain showed a buildup of electrical activity, called the readiness potential, about 550 milliseconds before the person actually moved their wrist. That wasn't surprising. Scientists had known about the readiness potential since the 1960s. What was surprising was the timing of the conscious intention. The subjects reported feeling the urge to move about 200 milliseconds before the movement. But that was a full 350 milliseconds after the brain had already started preparing. In other words, the brain seemed to decide to move before the person was consciously aware of deciding. The unconscious machinery was already in motion before the feeling of choosing arrived. Now, you might be thinking, wait, does that mean free will is an illusion? That's exactly what a lot of people took from Libet's experiment, and it set off a firestorm of debate that's still going on today. Libet himself was more cautious. He pointed out that even though the brain started the process unconsciously, the conscious mind still had time to veto the action, to override the impulse before it became a movement. He called this free won't instead of free will. But the deeper implication was what mattered for consciousness science. Libet had shown that you could design a rigorous experiment that poked directly at the relationship between brain activity and conscious experience. You could put a number on the timing of awareness. You could measure something about consciousness itself, not just behavior, not just cognitive processing, but the subjective moment of becoming aware. That was a crack in the wall, and through that crack, a whole generation of researchers started to squeeze. By the late 1980s and early 90s, consciousness was becoming respectable again. Francis Crick, the same Francis Crick who had co-discovered the structure of DNA, turned his attention to consciousness in his later career. Working with the neuroscientist Christoph Koch at Caltech, Crick proposed that instead of trying to solve the whole mystery at once, scientists should look for what he called the neural correlates of consciousness, the NCC. The idea was pragmatic and almost engineering-like in its approach. Don't ask what consciousness is. Don't ask how matter becomes experience. Just ask, what's happening in the brain when a specific conscious experience occurs, and what's different when that experience is absent? This was a brilliant reframing, because it turned an impossible philosophical question into a tractable scientific one. You don't need to solve the hard problem to find neural correlates. You just need good experiments. And one of the best tools for this turned out to be something you've probably experienced yourself: binocular rivalry. Here's how it works. If you show one image to a person's left eye and a completely different image to their right eye, the brain can't fuse them into a single picture. Instead, perception alternates. You see one image for a few seconds, then it fades and the other one appears, then it switches back. The physical stimulus never changes. Both images are hitting your retinas the whole time, but your conscious experience flips back and forth. So if you're monitoring brain activity during binocular rivalry, you can look for neurons that track the stimulus, that fire regardless of which image the person is seeing, and neurons that track the percept, that fire only when the person is consciously aware of one image versus the other. The neurons that track the percept, those are your candidates for neural correlates of consciousness. Koch and Crick spent years on this kind of work, and they weren't alone. Stanislas Dehaene in Paris, Giulio Tononi in Madison, Wisconsin, Bernard Bars, who had proposed something called Global Workspace Theory. All of these researchers were converging on the same frontier from different angles, and what they were finding was that consciousness doesn't seem to live in any single spot in the brain. It's not like there's a consciousness center that lights up when you're aware and goes dark when you're not. Instead, the emerging picture was more like a network phenomenon, something that happens when certain patterns of activity spread across the brain in particular ways, linking distant regions into a temporary, unified whole. And this is where the real theories start to take shape, the ones that are still competing with each other right now, the ones that researchers are designing experiments to test as we speak. One of the most influential is that global workspace theory I just mentioned, and to understand it, think about something surprisingly ordinary. Think about what happens when you're driving a familiar route and your mind wanders, and then suddenly a child runs into the road and everything snaps into focus. In that instant, something changed in your brain. Information that was being processed locally and unconsciously, the visual scene, the motor commands for steering, the sound of the engine, suddenly got broadcast widely, made available to many different systems all at once. Your planning centers, your memory systems, your language areas, your emotional circuits, all of them suddenly got access to the same piece of information at the same time. That child in the road went from being just another bit of visual data processed in the back of your brain to being the single most important thing in your entire mental world. And that transition, that shift from local processing to global broadcasting, that, according to global workspace theory, is what consciousness actually is. Bernard Bars first proposed this idea back in 1988, and it's one of those concepts that sounds almost too simple at first, but gets more powerful the longer you sit with it. Here's the analogy he used. Imagine a theater, a big, dark theater with a huge stage. On that stage, there's a single bright spotlight. The spotlight can only illuminate one thing at a time, maybe an actor, maybe a prop, maybe a scene. Whatever's in the spotlight, that's what the entire audience can see. Now, behind the scenes, there are all sorts of things happening. Stagehands moving sets, directors making decisions, lighting technicians adjusting equipment. But the audience doesn't see any of that. The audience only sees what's in the spotlight. In Bars' model, the spotlight is consciousness. The stage is working memory, that limited workspace where you hold things you're actively thinking about. The audience represents all those unconscious processors distributed throughout the brain, the ones that can receive the broadcast and act on it. And the stagehands, the directors, the technicians backstage. Those are the unconscious mechanisms that decide what gets into the spotlight in the first place. So consciousness, in this view, isn't doing all the work. Most of the work is happening in the dark, behind the scenes. Consciousness is just the broadcast mechanism, the thing that takes a selected piece of information and makes it globally available. And here's what's really clever about this framework. It explains why consciousness has the properties it does. Think about it. Why can you only be conscious of a few things at once? Because the spotlight is narrow. Why does it take effort to hold something in awareness? Because maintaining a global broadcast takes coordination. Why do things sometimes pop into consciousness seemingly out of nowhere? A solution to a problem you weren't actively thinking about. A memory triggered by a smell. Because the backstage processes are always working, and sometimes they push something into the spotlight without you deliberately directing it there. Now, Stanislas Dehaene took this theater metaphor and gave it teeth. Real neuroscientific teeth. Working at the Collège de France and the Neurospin Brain Imaging Center outside Paris, Dehaene spent decades looking at what actually happens in the brain when information crosses that threshold from unconscious to conscious processing. And what he found, using techniques like functional MRI and electroencephalography, was remarkably consistent with the workspace idea. When a stimulus is processed unconsciously, say a word flashed on a screen so briefly that you don't report seeing it, you get localized brain activity. The visual cortex responds. Maybe some language areas respond, but the activity stays contained, like a small fire that doesn't spread. However, when the same stimulus crosses the threshold into conscious awareness, when you actually see the word and can report it, something dramatically different happens. You get what Dehaene calls ignition, a sudden, explosive spread of activity across the brain, linking the prefrontal cortex, the parietal cortex, the temporal regions, all firing together in a synchronized, reverberating pattern. It's like the difference between a match that flickers and goes out versus a match that catches the kindling and suddenly the whole campfire is blazing. Dehaene published a landmark paper in 2001 with Jean-Pierre Changeau laying out this neural global workspace model, and one of the most compelling pieces of evidence came from studies of what's called the attentional blink. Here's how it works. You show someone a rapid stream of letters or numbers on a screen, one after another, very fast. You tell them to watch for two specific targets. Say, a white letter among black ones. If the two targets appear more than about half a second apart, people catch both of them just fine. But if the second target appears within about 200 to 500 milliseconds of the first, something strange happens. People often miss it entirely. They just don't see it. It's as if the brain's global workspace is occupied with processing the first target, broadcasting it to all those systems, and during that broadcast, the workspace is temporarily unavailable. The second target arrives, gets processed locally, but never makes it into the spotlight. It stays unconscious. And sure enough, when you look at the brain activity, the missed targets show local processing, but no ignition, no global broadcast. The seen targets show that distinctive widespread activation pattern. So that's one major theory, consciousness as global broadcast. And it's powerful because it's testable. It makes specific predictions, and it maps onto real neural mechanisms. But it's not the only game in town, and this is where the story gets really interesting, because the main rival theory comes from a completely different direction and makes some genuinely strange claims. Giulio Tononi is an Italian neuroscientist who trained with Gerald Edelman, a Nobel laureate who himself had fascinating ideas about consciousness and neural Darwinism, and then moved to the University of Wisconsin-Madison, where he developed something called Integrated Information Theory, or IIT for short. And IIT doesn't start where you might expect. It doesn't start with the brain at all. It starts with consciousness itself, with the experience, and works backward to ask what kind of physical system could possibly generate it. Tononi's approach was almost mathematical, almost philosophical in its foundations. He began by identifying what he considered the essential properties of any conscious experience. And he came up with a set of axioms, things that are self-evidently true about experience from the inside. First, every conscious experience exists. It's real. It's there. You can't deny it. That's basically Descartes' insight, right? Second, every experience is structured. It has a specific shape, a specific quality. Seeing a red circle is different from hearing a C-sharp, which is different from feeling anxious. Third, every experience is specific. It is this experience and not any of the countless other experiences it could have been. Fourth, every experience is unified. You don't experience the color of an object separately from its shape. You experience one integrated scene. And fifth, every experience is definite. It has certain contents and borders. It includes some things and excludes others. Now here's where Tononi does something bold. He takes these axioms about experience and translates them into requirements for any physical system that could generate consciousness. And the key requirement, the one that gives the theory its name, is integration. A conscious system, Tononi argues, must integrate information. It must be a system where the whole is more than the sum of its parts, where the different components are so interconnected that you can't divide the system into independent pieces without losing something. And he formalized this with a mathematical quantity he calls phi, the Greek letter phi. Phi measures how much integrated information a system generates. The higher the phi, the more conscious the system is, according to IIT. And this is where things get genuinely provocative, because if you take IIT seriously, really seriously, it leads to some conclusions that make a lot of people uncomfortable. For one thing, it implies that consciousness isn't exclusive to brains. Any system that integrates information in the right way, that has a high enough phi, would have some degree of consciousness. A thermostat, in this view, might have an almost infinitesimally tiny flicker of experience. Not anything like human consciousness, but not zero either. This is a form of panpsychism, the idea that consciousness is a fundamental feature of certain physical arrangements, and it's baked right into the mathematics of IIT. Some researchers find this elegant and even beautiful. Others find it absurd. And that tension, that disagreement, is one of the most alive debates in all of science right now. But here's what makes IIT more than just philosophy. Tononi and his collaborators, particularly Marcello Massimini, developed a way to actually measure something related to phi in real human brains. They couldn't compute phi directly. The calculation is astronomically complex for a system with billions of neurons. But they came up with a proxy. The technique is called zap and zip. You zap the brain with a pulse of transcranial magnetic stimulation, basically a brief magnetic field that triggers a wave of neural activity. And then you record the brain's electrical response with EEG. Then you compress the data like zipping a computer file. The idea is that if the brain's response is complex and integrated, if different parts of the brain respond in different but coordinated ways, then the compressed data will still be large, because there's a lot of information that can't be simplified away. But if the brain's response is simple and stereotyped, or if different regions respond independently without integration, the compressed data will be small. And when they tested this on people in different states of consciousness, the results were striking. Awake, healthy people had high complexity scores. People under general anesthesia, propofol, xenon, midazolam, it didn't matter which drug, had dramatically lower scores. People in dreamless sleep, low scores. People in REM sleep, dreaming, scores that bounced back up close to waking levels. And here's where it gets clinically meaningful. Patients in vegetative states, people who showed no outward signs of consciousness, sometimes had high complexity scores, suggesting there might be awareness trapped inside an unresponsive body. This wasn't just theoretical anymore. This was a tool that could potentially tell you whether someone was conscious when they couldn't tell you themselves. So now you've got these two major theories sitting across from each other. Global Workspace Theory says, consciousness is about broadcasting information widely across the brain. Integrated information theory says consciousness is about how much integrated information a system generates, regardless of broadcasting. They agree on some things. Both predict that widespread, coordinated brain activity is associated with consciousness. But they disagree on deep questions. They disagree about what consciousness fundamentally is. They disagree about whether a computer running the right algorithm could be conscious. Global Workspace Theory would say, yes, in principle. If the functional architecture is right, the substrate doesn't matter. IIT would say it depends on the physical structure, on the actual causal relationships between components, and that a digital simulation of a brain, even a perfect one, might have zero consciousness because the integrated information structure is different. And in 2019, something remarkable happened. A group of researchers, frustrated by decades of theoretical debate with no resolution, launched what might be the most ambitious consciousness experiment ever attempted. It was called the Adversarial Collaboration, and it was funded partly by the Templeton World Charity Foundation. The idea was beautifully simple and also kind of radical for science. Take the two leading theories, Global Workspace Theory and IIT, sit the proponents down together, and design experiments that would produce different predictions depending on which theory was correct. Not experiments designed to confirm one theory, but experiments specifically designed to distinguish between them. Dehaney's camp and Tononi's camp, working together with a neutral team, agreeing in advance on what results would count as evidence for or against each theory. The first results came out in 2023, and they were fascinating, and also in that wonderfully honest way that real science works, not entirely clean. Some predictions from IIT were not supported. Specifically, the theory predicted sustained activity in the posterior cortex during conscious perception, and the evidence for that was mixed. Global Workspace Theory's predictions about prefrontal involvement also didn't hold up as cleanly as expected. Neither theory got a clean win. Neither theory was knocked out. And that might sound disappointing, but actually, think about what that means. It means we're at exactly the kind of moment in science where the real breakthroughs tend to happen, where the existing frameworks are being tested against reality and found to be incomplete, where something new is needed, something that maybe takes pieces from both and assembles them into something we haven't quite imagined yet. And that's not just optimism talking. That's the pattern of how science actually moves forward. You rarely get a moment where one grand theory sweeps everything else away. What usually happens is messier and, honestly, more interesting. You get partial confirmations, unexpected results, and then somebody comes along and reframes the whole question in a way that makes the old debate look slightly beside the point. So let's sit with that for a moment, because the aftermath of the 2023 Adversarial Collaboration results is genuinely one of the most exciting periods in consciousness science. And to understand why, you need to appreciate what those results actually revealed beyond the headline of neither theory won. One of the specific experiments involved showing people images, faces, objects, patterns, and tracking brain activity with both fMRI and EEG simultaneously. The idea was to catch consciousness in the act, right at the moment when a stimulus crosses the threshold from unconscious processing to conscious awareness. Now, Global Workspace Theory predicted that you'd see a burst of activity in the prefrontal cortex, that ignition we talked about earlier, the moment the information gets broadcast across the brain's workspace. IIT predicted something different. It predicted that the sustained experience of seeing, say, a face would be reflected in ongoing activity in the posterior cortex, the back of the brain, where sensory processing and integration happen, and that this activity would persist for as long as the conscious experience lasted, not just as a brief flash. Here's what actually showed up. The sustained posterior activity that IIT predicted? It was there, but it was more complicated than the theory suggested. The activity patterns didn't map onto the specific mathematical structures that IIT said they should. And the prefrontal ignition that Global Workspace Theory predicted? It was there too, but it seemed to be more related to reporting the experience, to the act of saying, yes, I saw it, than to the experience itself. And that distinction, subtle as it sounds, is actually huge, because it raises a question that had been lurking in the background of consciousness research for years. When we measure brain activity during conscious experience, how much of what we're seeing is consciousness itself, and how much is just the cognitive machinery of noticing, attending to, and reporting on that consciousness. This is sometimes called the problem of the no-report paradigm, and it's one of those methodological puzzles that sounds technical, but is actually deeply philosophical. Think about it this way. Every experiment on consciousness, at some point, requires the subject to tell you what they experienced. Press a button when you see the image. Say whether the stimulus was on the left or the right. Rate how vivid the experience was. But the act of reporting requires attention, decision-making, working memory, motor planning, all of which light up the brain in ways that have nothing to do with the raw experience itself. It's like trying to measure the weight of a butterfly by putting it on a scale that also has a brick on it. You're always measuring the butterfly plus the brick, and you're never quite sure how much of the reading is butterfly. Some researchers, and this is where it gets really interesting, started designing experiments where they could infer that a person was having a conscious experience without requiring them to report it. One clever approach uses eye tracking. You can tell from someone's pupil dilation and gaze patterns whether they've consciously perceived a change in a visual scene, even if you never ask them about it. Another approach uses a technique where you present stimuli during a task and then test for the effects of that stimulus later, inferring conscious perception from its downstream influence on behavior, rather than from a direct report. And when you strip away the reporting, some of that prefrontal activity diminishes, which suggests, and this is still debated, nothing is settled here, that at least some of what Global Workspace Theory was pointing to as the signature of consciousness might actually be the signature of cognitive access, of the brain's machinery for grabbing hold of an experience and doing something with it. Consciousness itself, the raw feel of it, might be happening somewhere else, or in a different way, or might not require that prefrontal broadcast at all. Now, you might be thinking, does this mean IIT was right all along? Not exactly. Because IIT's specific predictions about the mathematical structure of posterior cortical activity didn't hold up either. What seems to be emerging is something more nuanced. The posterior cortex does seem deeply involved in the content of conscious experience, in what you're experiencing, but the way it's involved doesn't perfectly match any existing theory's predictions. And this is where a new generation of theories starts to enter the picture. One of the most talked about is called the higher order theory of consciousness, and it has roots going back to the philosopher David Rosenthal, who's been developing these ideas since the 1980s and 1990s at the City University of New York. The core idea is deceptively simple. A mental state becomes conscious when there is a higher order representation of that state, when the brain not only processes information, but also represents to itself that it is processing that information. You don't just see red. Some part of your brain represents the fact that you are seeing red. And it's that second-order representation, that mental state about a mental state, that constitutes consciousness. Think of it like this. Imagine you're walking through a forest, and your visual system is processing all the greens and browns and dappled light. That processing is happening regardless, but you become conscious of the beauty of the scene when some other part of your brain, a higher order system, generates a representation that says, in effect, I am currently having this visual experience. Without that higher order thought, the processing still happens, but nobody's home to notice it. It's the difference between a security camera recording a room and a person actually watching the monitor. Rosenthal's version of this is quite specific. He argues that these higher order representations are thoughts, actual cognitive states with conceptual content. But other researchers have developed softer versions. Hakwon Lau, a neuroscientist who's worked at UCLA and now at Riken in Japan, has developed a version he calls the perceptual reality monitoring theory, which proposes that consciousness arises when the brain's monitoring systems generate a kind of model of its own perceptual states. It's not necessarily a full-blown thought. It's more like the brain running a check on its own signal quality, asking, is this perception reliable? Is this real? And when that monitoring process kicks in, you get conscious experience. When it doesn't, when the signal is processed but not monitored, you get unconscious processing. Here's what's clever about this approach. It actually predicts something testable about the prefrontal cortex. Higher order theories generally place the seat of consciousness, or at least the mechanism that makes experience conscious, in the prefrontal regions, because that's where the brain does its monitoring, its metacognition, its thinking about thinking. But unlike global workspace theory, higher order theories don't necessarily predict the dramatic, widespread broadcast. They predict something more targeted. Activity in specific prefrontal areas that are involved in self-monitoring, not the whole frontal lobe lighting up like a Christmas tree. And some of the adversarial collaboration data actually fits this picture better than either of the two theories that were officially being tested. Which is a beautiful irony. You set up an experiment to test theory A against theory B, and the results end up pointing toward theory C. But let's not get ahead of ourselves, because there's another framework that's been gaining enormous traction, and it comes from a completely different direction. It's called predictive processing, or sometimes the predictive brain hypothesis, and its most prominent champion is Carl Friston, a neuroscientist at University College London, who is, and I say this with genuine admiration, one of the most brilliant and also most difficult to understand thinkers in all of neuroscience. Friston's work is built on a mathematical framework called the free energy principle, and explaining it fully would take us down a very deep rabbit hole, but the core intuition is actually quite beautiful. The brain, Friston argues, is fundamentally a prediction machine. It doesn't passively receive information from the world and then figure out what's happening. Instead, it's constantly generating predictions about what it expects to perceive, sending those predictions down to the sensory systems, and then only paying attention to the prediction errors, the differences between what it expected and what actually showed up. You've experienced this directly. Think about driving a familiar route home. You barely notice the road, the turns, the traffic lights. Your brain is predicting all of it so accurately that there's almost nothing surprising, almost no prediction error. And so you arrive home with barely any conscious memory of the drive. But if a deer suddenly jumps into the road, that massive prediction error floods your awareness. Suddenly, you're intensely, vividly conscious of the road, the animal, the distance, the brake pedal. Consciousness in this framework isn't about receiving information. It's about the brain's relationship to surprise. Now, Friston himself is somewhat cautious about making strong claims about consciousness specifically. The free energy principle is really a theory about how brains work in general, about perception, action, learning, everything. But a number of researchers have started building explicit theories of consciousness on top of this predictive processing framework. One of the most compelling is Anil Seth, a neuroscientist at the University of Sussex in England, who has developed what he calls a beast machine theory of consciousness. Seth's argument is that consciousness is what happens when the brain generates predictions not just about the external world, but about the body itself, about its own internal states, its heartbeat, its breathing, its gut feelings, its sense of being a living organism. This is where things get really profound, because Seth is essentially proposing that the most basic form of consciousness isn't seeing or hearing or thinking. It's the felt sense of being alive. The background hum of bodily existence that you almost never notice, but that underlies everything else. Your experience of being you, right now, listening to this, isn't primarily constructed from what your eyes and ears are telling you. It's constructed from your brain's best guess about the state of your body, your brain's ongoing prediction about what it's like to be this particular living organism in this particular moment. And that connects to something really old, actually, something that William James, remember him, back at the very beginning of scientific psychology, wrote about in the 1880s. James argued that emotions aren't caused by our perceptions of events. Instead, he said, we perceive the event, our body reacts, and then we experience the emotion as our brain's interpretation of those bodily changes. You don't run from the bear because you're afraid. You're afraid because you're running. That idea was controversial then, and it's still debated now, but Seth's predictive processing framework gives it a new and more sophisticated foundation. Your emotional experience, your felt sense of what's happening, is your brain's prediction about why your body is in the state it's in. And here's where Seth's work connects back to the practical, clinical side of consciousness research. Because if consciousness is fundamentally about the brain's predictive models of the world, of the body, of the self, then altered states of consciousness should correspond to changes in those predictive models. And that's exactly what researchers are finding when they study psychedelic drugs. This might seem like a strange turn, but stay with me, because the neuroscience of psychedelics has become one of the most productive windows into consciousness in the last decade. Substances like psilocybin, LSD, and DMT have profound effects on conscious experience. They alter perception, dissolve the sense of self, create experiences that people describe as among the most meaningful of their lives. And when you look at what these substances do in the brain, the picture that emerges is remarkably consistent with the predictive processing framework. Most classic psychedelics work primarily by activating a specific type of serotonin receptor called 5-HT2A. And these receptors are densely concentrated in the cortex, particularly in the layers of neurons that are responsible for sending those top-down predictions we were just talking about. What psychedelics seem to do at the neural level is disrupt the brain's prediction machinery. They turn down the volume on the brain's confident expectations about what it's going to perceive and what the world is like. And when those predictions weaken, the prediction errors, the raw, surprising, unfiltered signals from the senses flood in. the world becomes overwhelming, novel, strange, beautiful, terrifying, because the brain's usual trick of smoothing everything into a familiar, predicted reality has been temporarily disabled. Robin Carhart Harris, who was at Imperial College London and is now at UC San Francisco, has formalized this in what he calls the rebus model, relaxed beliefs under psychedelics. The beliefs here aren't conscious beliefs like, I believe the earth is round. They're the deep, automatic, predictive models that the brain uses to construct your entire experience of reality, including your experience of having a self. And when those models relax, when those predictions loosen their grip, consciousness doesn't disappear. It transforms. It becomes more fluid, more uncertain, more open. The boundaries between self and world become less defined, and that dissolution of the predictive self model is what people are describing when they talk about ego dissolution, that feeling of the boundaries of the self becoming transparent, porous, sometimes vanishing altogether. You stop knowing where you end and the room begins. The narrative that usually runs in your head, the story of who you are, what you want, what you're afraid of, that narrative loosens, and for a while, you're just awareness, raw, unstructured, sometimes ecstatic, sometimes terrifying awareness without the usual scaffolding of selfhood holding it all in place. And here's what's so valuable about this for consciousness science. For decades, researchers have been trying to study consciousness by looking at what happens when it turns on or off. Sleep, anesthesia, coma. Those are useful contrasts, but they're blunt instruments. What psychedelics offer is something much more precise. They don't turn consciousness off. They twist it. They change its character while leaving the person awake, responsive, able to report what they're experiencing. That gives you a window into the internal structure of conscious experience that you simply can't get any other way. And the neuroimaging data from psychedelic studies has been genuinely surprising. You might expect that these incredibly vivid, overwhelming experiences would show up as increased brain activity, more firing, more energy, more everything. But that's not what researchers found. When Carhart Harris and his team did some of the first modern fMRI studies with psilocybin, published around 2012, what they saw was primarily decreases in activity, particularly in a network called the default mode network. Now, the default mode network is one of those discoveries that reshaped how we think about the brain. It was identified in the early 2000s, largely through the work of Marcus Rachel at Washington University in St. Louis, and it refers to a set of brain regions, medial prefrontal cortex, posterior cingulate cortex, parts of the temporal lobe, that are most active when you're not doing any particular task, when you're daydreaming, when you're thinking about yourself, when you're ruminating about the past or imagining the future, when you're constructing that ongoing narrative of who you are. The default mode network, in a real sense, is the neural infrastructure of the self model. It's the machinery that maintains the story of you. And psychedelics quiet it down. They reduce the connectivity within that network. They decrease the blood flow to those regions, and the degree to which the default mode network is disrupted correlates with the intensity of ego dissolution that people report. The more the network is suppressed, the more the self dissolves. That's a remarkably clean relationship for something as messy and subjective as consciousness research. But here's the thing. While activity decreases in some networks, the overall pattern of brain connectivity becomes more entropic, more random, more flexible. Brain regions that don't normally talk to each other start communicating. The usual modular structure of brain networks, where visual areas talk mostly to other visual areas and motor areas talk mostly to other motor areas, that structure breaks down and you get this state of increased neural crosstalk. It's as if the brain's usual organizational chart gets temporarily dissolved and signals can flow along paths that are normally blocked. And that, Carhart-Harris argues, is why psychedelic experiences feel so novel, so creative, so synesthetic, because information is mixing in ways it normally can't. Now, I want to pause here and connect this back to something we talked about earlier, because it's one of those moments where different threads of consciousness research converge in a really satisfying way. Remember Giulio Tononi's integrated information theory? One of its core claims is that consciousness corresponds to integrated information. To the degree that a system is both differentiated, meaning it has many distinct states, and integrated, meaning all those states are bound together into a unified whole. Well, think about what psychedelics are doing. They're increasing differentiation. The brain is exploring a wider repertoire of states, becoming more entropic, more varied in its activity patterns. And they're also, at least temporarily, increasing a certain kind of integration, more crosstalk, more connections between distant regions. So, from an IIT perspective, you might predict that psychedelic states would involve high integrated information. And indeed, some researchers have tried to estimate measures related to phi during psychedelic states and found increases, though the technical challenges of actually computing phi for a whole brain remain enormous. And from the global workspace perspective, what's happening is equally interesting. The usual gatekeeping mechanisms that determine what information gets broadcast into the global workspace and what gets filtered out, those mechanisms are being weakened. More information is flooding in. The workspace is being overwhelmed with signals that would normally be suppressed, and that maps onto the subjective experience quite well. The feeling of being flooded with sensation, of every detail becoming significant, of the world becoming almost unbearably vivid and meaningful. So psychedelics are acting as a kind of natural experiment that tests multiple theories of consciousness simultaneously. And different theories make different predictions about what should happen, which means psychedelic neuroscience is becoming one of the most active battlegrounds for testing these frameworks against each other. But let's step back from the pharmacology for a moment, because there's another domain where consciousness science has been making remarkable progress, and it's one that affects you in the most intimate possible way. It's the question of consciousness during sleep. Right now, as you're lying there listening to this, you're probably somewhere on the edge between waking and sleeping, and what's happening in your brain as you make that transition is one of the most fascinating things in all of neuroscience. When you fall asleep, and I mean the moment you actually cross that threshold from wakefulness into the earliest stage of sleep, your conscious experience doesn't just gradually dim like a light on a dimmer switch. It does something much stranger. In the transition phase, which sleep researchers call the hypnagogic state, you often get these vivid, fragmentary experiences, flashes of imagery, snippets of conversation, bizarre micro-narratives that feel completely real for a moment and then dissolve. Your brain is still generating conscious experience, but the executive control systems that normally keep that experience organized and coherent are going offline. It's a little bit like what psychedelics do, actually. The prediction machinery is loosening its grip, and experience becomes more fluid and less constrained. And then, as you sink deeper into what's called slow-wave sleep, the deep, restorative stages, something remarkable happens. Those big, slow electrical waves that sweep across your cortex, the delta waves, They represent something very specific at the neural level. They're moments when large populations of neurons all go silent together, then all fire together in a synchronized rhythm. It's like a stadium wave at a sports event where everyone stands up and sits down in sequence. And Marcello Massimini, remember him, with the zap and zip technique, showed that during deep sleep, when you send a TMS pulse into the brain, the resulting electrical activity doesn't propagate in that complex, differentiated pattern you see during waking consciousness. Instead, it either stays local, dying out near where it started, or it spreads in a simple, stereotyped wave. The brain loses its ability to integrate information in a complex way, and that, according to both IIT and Global Workspace Theory, is why deep sleep is typically unconscious. Not because the brain is inactive, because it's actually quite active during slow-wave sleep, but because the activity has lost its complexity, its integration, its capacity to support the kind of differentiated yet unified information processing that consciousness requires. But, and this is where it gets really interesting, deep sleep isn't entirely unconscious. If you wake people up from slow-wave sleep and ask them, "Were you experiencing anything?" a surprising proportion of the time, some studies say around 30%, people will report some kind of experience. Usually it's vague, thought-like, less vivid than a dream, but it's something. There's something it's like to be in deep sleep, at least sometimes. And that creates a puzzle, because the standard neural signatures that we associate with consciousness, the complex integrated activity patterns, are largely absent during deep sleep. So either our measures aren't sensitive enough, or there's something about consciousness that can persist even when the usual neural correlates are diminished. And then there's dreaming, which is its own extraordinary phenomenon. During REM sleep, rapid eye movement sleep, the stage most associated with vivid dreaming, the brain's activity patterns look remarkably similar to waking consciousness in many ways. The EEG becomes desynchronized, fast, complex. Many of the same cortical regions that are active during waking perception become active during dreams. And yet the experience is profoundly different from waking life. You accept impossible things without question. Your critical thinking is largely offline. You have experiences that feel completely real in the moment, but that you recognize as bizarre the instant you wake up. What's going on there? Well, from a predictive processing perspective, dreaming is what happens when the brain's prediction machinery runs free without any constraining sensory input. During waking life, your brain is constantly generating predictions about what's going to happen next, and those predictions are being checked against actual sensory data. Light hitting your retinas, sounds entering your ears, pressure on your skin. The prediction errors keep the system honest, keep it tethered to reality. But during REM sleep, the thalamic gates that relay sensory information to the cortex are largely closed. The brain is generating predictions, constructing a model of reality, but there's no sensory data to correct it. So the model runs wild. It generates scenarios that are internally coherent enough to feel real, but that aren't constrained by any external reality check. That's a dream. And here's a detail that I find just endlessly fascinating. During REM sleep, there's a specific neurotransmitter that's almost completely absent from the brain, norepinephrine. During waking life, norepinephrine is involved in attention, alertness, and critically, in signaling surprise and novelty. It's part of the system that flags prediction errors. And during REM sleep, the neurons that produce norepinephrine, the locus coeruleus in the brainstem, go almost completely silent. So not only is sensory input blocked, but the very neurochemical system that would normally alert you to surprising or impossible events is turned off. That's why you don't notice the impossibilities in your dreams. The system that would normally say, "Wait, that doesn't make sense," is chemically disabled. Now, there's one more sleep phenomenon that brings all of this together in a particularly striking way, and it's one that some of you may have experienced yourselves. Lucid dreaming, the state where you're dreaming but you become aware that you're dreaming, and you can sometimes even control the dream. Lucid dreaming is fascinating for consciousness researchers because it represents a hybrid state. You have the vivid, immersive, hallucinatory experience of a dream, but you also have the metacognitive awareness, the self-reflective capacity that's normally associated with waking consciousness. You're conscious of being conscious, even while you're asleep. And when researchers have studied lucid dreaming in the lab, which is tricky because you need dreamers who can reliably become lucid and who can signal to the experimenters using pre-arranged eye movements, since eye movements are one of the few motor outputs that aren't paralyzed during REM sleep. What they've found is that lucid dreaming is associated with increased activity in the prefrontal cortex compared to ordinary dreaming. The frontal regions that support self-reflection, metacognition, and critical thinking partially reactivate during lucid dreams. And that brings us right back to the debate about the role of the prefrontal cortex in consciousness. Remember the question that came out of the Templeton collaboration: whether prefrontal activity is necessary for consciousness itself, or only for the higher order awareness of consciousness, the reporting and reflecting. Lucid dreaming suggests that there might be a real, experiential difference between consciousness with prefrontal involvement and consciousness without it. Ordinary dreams are conscious experiences. There's something it's like to dream, but they lack the self-reflective, metacognitive quality that comes with prefrontal engagement. Lucid dreams have both. And this connects to an even deeper question, one that has been simmering in the background of everything we've been talking about. And it's a question that some researchers think might be the most important one of all. It's the question of what consciousness is actually for. Not what it is, not how it arises, but what it does, what function it serves. Because if consciousness is just an epiphenomenon, just a byproduct of neural processing that doesn't actually influence behavior, then it's hard to see how evolution would have shaped it, refined it, made it so elaborate and metabolically expensive. But if consciousness does something, if it plays a functional role in guiding behavior, in making decisions, in learning from experience, then we should be able to identify what that role is and understand why some processes are conscious and others aren't. And this is where a researcher named Michael Graziano at Princeton enters the picture, with a theory that takes a completely different approach from anything we've discussed so far. Graziano's starting point isn't philosophy or physics or information theory. His starting point is attention. Plain old attention. The neuroscience of how your brain tracks objects, monitors other agents, and models the world around you. And that might sound like a strange place to start a theory of consciousness, but once you hear where he takes it, it's genuinely one of the most elegant proposals out there. Graziano's idea is called the attention schema theory, and he first laid it out in detail around 2013. Here's the core insight. Your brain has this remarkable ability to construct internal models of things. It builds a model of your body. That's your body schema. The reason you can close your eyes and still know where your hand is. It builds models of the physical world around you. That's how you can catch a ball without consciously computing trajectories. And Graziano's proposal is that your brain also builds a model of its own attention. Just like it models your arm or a flying ball, it constructs a simplified, schematic representation of what attention is and what it's doing at any given moment. And that model, that internal description your brain writes of its own attentional processes, is what we experience as consciousness. Let that sit for a second. The claim is that consciousness is essentially your brain's cartoon-like sketch of its own attention. Not attention itself, but the model of attention. And just like your body schema is a useful simplification, it doesn't represent every muscle fiber and tendon, just a rough map of where your limbs are. The attention schema is a useful simplification that doesn't capture the actual neural machinery of attention. It captures something much vaguer, something more like an inner essence, a felt quality, a subjective experience. And Graziano's argument is that this is exactly why consciousness seems so mysterious to us. We're introspecting on a model, not on the actual mechanism. It's like asking a person to describe how their arm works based only on their body schema. They'd tell you about reaching and grasping, but they wouldn't know anything about motor neurons or muscle fibers, because the schema doesn't contain that information. In the same way, when you introspect on your own consciousness, you're consulting the attention schema, and it tells you something like, I have this inner awareness, this subjective experience, but it can't tell you how it's produced, because the schema was never designed to represent the mechanism. It was designed to be useful, not accurate. And this is where Graziano makes a really provocative move. He says the hard problem of consciousness, that seemingly impossible gap between physical processes and subjective experience that Chalmers identified, isn't actually a deep metaphysical mystery. It's an artifact of the attention schema being a simplified, incomplete model. The reason we can't figure out how physical stuff gives rise to subjective experience is that subjective experience, as we conceive of it, is a description generated by an internal model that deliberately leaves out the physical details. We're trying to bridge a gap that our own cognitive architecture created. It's not that the gap is unbridgeable in reality, it's that the model we're using to look at the problem is the very thing generating the illusion of the gap. Now you might be thinking, this sounds a bit like Dennett. Consciousness as a kind of cognitive illusion, something the brain constructs rather than something metaphysically fundamental. And you'd be right, there are strong family resemblances. But Graziano is more specific about the mechanism. He's not just saying consciousness is an illusion in some vague sense. He's saying here is the specific computational function, attention modeling. And here is why it produces the specific kind of illusion it does. And he's grounded this in the neuroscience of attention, particularly in work on how the brain controls and prioritizes signals. Think about what attention actually does in the brain. At any given moment, you're being bombarded with vastly more sensory information than you can process. Your visual system alone is receiving an enormous flood of data. Attention is the process by which certain signals get boosted. They win the competition for processing resources, while other signals get suppressed. This is well-established neuroscience, going back to work by researchers like Anne Treisman in the 1960s and Michael Posner in the 1970s and 80s. Attention is real, it's measurable, and it has clear neural correlates in areas like the temporoparietal junction, the superior colliculus, and various prefrontal regions. Graziano's insight is that to control attention effectively, the brain needs a model of it. This is a general principle in control theory. To control any complex process, it helps enormously to have an internal model of that process. Engineers use this principle all the time. If you're building a robot arm and you want it to move precisely, you give the control system an internal model of the arm's dynamics, its mass, its joint angles, its momentum. The model doesn't have to be perfect. It just has to be good enough to allow effective control. And the brain does the same thing with attention. It builds a model of what attention is doing, what it's focused on, how strongly, what's being filtered out, and uses that model to regulate and adjust attentional processes in real time. And here's the thing that makes this theory so interesting for the question of what consciousness is for. If consciousness is the attention schema, then it has a clear functional role. It's the brain's control model for attention. It exists because organisms that could model and regulate their own attention had a survival advantage over organisms that couldn't. You can see how this would matter. An animal that can flexibly shift attention from the rustling in the bushes to the shadow overhead to the scent on the wind, and that has an internal model allowing it to monitor and optimize those shifts, is going to be better at detecting predators, finding food, navigating social hierarchies. Consciousness, in this view, isn't an accidental byproduct. It's a control mechanism that evolution built because it was useful. And Graziano extends this in a really fascinating direction, towards social cognition. Because here's what's wild. Your brain doesn't just model your own attention, it also models other agents' attention. When you look at someone and notice that they're staring at something, you automatically construct a model of their attentional state. You infer what they're paying attention to, what they might be thinking about, what they're aware of. This is closely related to what psychologists call theory of mind, the ability to attribute mental states to others. And Graziano argues that the same machinery that generates your model of your own attention, your consciousness, is the machinery that allows you to model other minds. Consciousness and social cognition are two sides of the same coin. The brain evolved attention modeling partly to predict the behavior of other agents, and the self-directed version of that modeling is what we experience as our own awareness. This connects to some really interesting developmental and comparative evidence. Human infants develop the ability to follow others' gaze, to model where someone else is paying attention, around 9 to 12 months of age, and this capacity is closely linked to the later development of theory of mind, which typically matures around age 4. And across species, the animals that show the most sophisticated social cognition, primates, corvids, some cetaceans, are also the ones where researchers have the strongest behavioral evidence for something like self-awareness. That's not proof of Graziano's theory, but it's suggestive. It hints that consciousness and social intelligence might have co-evolved, each driving the development of the other. Now, the attention schema theory has its critics, and the criticisms are worth thinking about. One common objection is that it doesn't really solve the hard problem so much as dissolve it. It says the problem is based on a misunderstanding, which some philosophers find deeply unsatisfying. If you're convinced that subjective experience is a real phenomenon that needs explaining, being told it's a modeling artifact might feel like a dodge. Another criticism is that attention and consciousness, while closely related, aren't identical. There's evidence from studies of inattentional blindness and subliminal perception, suggesting that you can have attention without awareness, and possibly awareness without attention, which complicates the picture. Graziano would respond that the theory is about the model of attention, not attention itself, so these dissociations don't necessarily pose a problem. But the debate continues. What I find most compelling about Graziano's approach is how it reframes the entire conversation. Instead of asking, how does the brain generate subjective experience? A question that might be unanswerable in its current form, it asks, why does the brain describe itself as having subjective experience? And that second question is a tractable scientific question. You can investigate it with the tools of neuroscience, psychology, and computational modeling. You can build artificial systems with attention schemas and see if they exhibit the kinds of self-reports that we associate with consciousness. Graziano has actually done some of this work, building simple computational models that, when equipped with an attention schema, make claims about having inner experiences, not because they actually do, but because their internal model describes their processing in those terms. And this brings us to one of the most charged frontiers in consciousness research right now: artificial intelligence and the question of machine consciousness. Because if consciousness is fundamentally about information integration, as Tononi's IIT suggests, or about global broadcasting, as Bars and Dehaney propose, or about attention modeling, as Graziano argues, then, in principle, there's nothing that restricts it to biological brains. Any system with the right architecture could potentially be conscious. And with the rapid development of large language models and other AI systems in the 2020s, this has gone from a philosophical thought experiment to something that feels urgently practical. You might remember John Searle's Chinese room argument from decades ago. The idea that a system can manipulate symbols without understanding them, that computation alone isn't sufficient for genuine understanding or consciousness. That argument is still very much alive in these debates. But the landscape has shifted. When Searle proposed the Chinese room in 1980, the AI systems of the day were rigid, rule-following programs that nobody seriously mistook for conscious. Today's large language models produce outputs that are fluid, contextual, sometimes eerily insightful, and millions of people interact with them daily. In 2022, a Google engineer named Blake Lemoine made headlines by claiming that LaMDA, one of Google's language models, was sentient. He was placed on administrative leave and eventually fired. Most AI researchers and consciousness scientists disagreed with his assessment, but the episode highlighted something important. We don't actually have agreed-upon criteria for determining whether a system is conscious. We don't have a consciousness meter. And the theories we've been discussing all night point in different directions on this question. IIT, for instance, would say that current AI architectures, including transformer-based language models, almost certainly have very low phi because their information processing, while powerful, isn't integrated in the deeply recurrent, densely interconnected way that biological neural networks are. A transformer processes information in relatively modular feed-forward sweeps. Tononi himself has argued that digital computers, no matter how sophisticated their outputs, are likely not conscious in any meaningful sense, because their architecture doesn't support the kind of integrated information that consciousness requires. The Global Workspace Theory might give a different answer. If an AI system has something functionally analogous to a global workspace, a mechanism for broadcasting selected information widely across its processing modules, then maybe it has something analogous to consciousness. And Graziano's theory suggests yet another criterion. Does the system model its own attentional processes? Does it have an internal representation of its own awareness? These aren't just academic questions anymore. As AI systems become more integrated into healthcare, criminal justice, education, and daily life, the question of whether they have any form of inner experience starts to matter ethically. And it matters in the other direction too. Understanding what makes biological consciousness special, if anything, helps us understand ourselves. It forces us to be precise about what we mean when we talk about awareness, experience, understanding, feeling. And this connects to another frontier that's been developing quietly alongside the AI debate, the science of consciousness in non-human animals. Because the same question applies. Which creatures are conscious? And how would we know? For a long time, science was cautious about attributing consciousness to animals, partly because of the behaviorist legacy, partly because of genuine uncertainty about how to test for it. But in 2012, a group of prominent neuroscientists gathered at the University of Cambridge and signed what's known as the Cambridge Declaration on Consciousness, which stated that the weight of evidence indicates that humans are not unique in possessing the neurological substrates that generate consciousness. The declaration specifically included all mammals, birds, and many other creatures, including octopuses. And the evidence they cited wasn't just behavioral, it was neuroanatomical and neurophysiological. Many of the brain structures and neurochemical systems associated with conscious experience in humans are present, in some form, across a wide range of species. But here's where it gets really interesting and really challenging. An octopus has about 500 million neurons, roughly the same as a dog, but its nervous system is organized in a radically different way. About 2/3 of an octopus's neurons are in its arms, not in its central brain. Each arm has a degree of autonomous control, able to taste, touch, and even make decisions semi-independently. So when we ask whether an octopus is conscious, we're not just asking yes or no. We're asking what kind of consciousness, distributed how, experienced in what way. And our theories give us different handles on this. IIT would say look at the integrated information across the whole system. Is there a unified phi, or are the arms their own little islands of integration? The Global Workspace Theory would ask whether there's a central broadcasting mechanism that creates a unified scene. Graziano might ask whether the octopus models its own attention. And this question of animal consciousness leads naturally into something even more fundamental: the question of how consciousness evolved in the first place. Because if consciousness serves a function, as Graziano and others argue, then it must have emerged at some point in evolutionary history. It wasn't always there. There was a time when life on Earth consisted entirely of organisms with no inner experience whatsoever. Single-celled creatures responding to chemical gradients, no more conscious than a thermostat. And then, somewhere along the way, something changed. Some organisms began to have experiences. There was something it was like to be them. When did that happen? What drove it? And what were the intermediate steps between no consciousness at all and the rich, vivid, self-reflective awareness that you're experiencing right now? Lying here in the dark, listening to these words? Some researchers have tried to pin down the transition point. Simona Ginsberg and Eva Jablonka, in their 2019 book, proposed that the key marker is something they call unlimited associative learning, the ability to learn novel associations between compound stimuli and outcomes across multiple sensory modalities. They argue that this kind of learning requires a form of experiencing, a minimal consciousness, and that it first appeared in the Cambrian explosion, roughly 540 million years ago, when animal body plans diversified explosively and nervous systems became significantly more complex. If they're right, then consciousness is ancient, far older than mammals, older than dinosaurs, older than fish as we know them. It arose in the warm, shallow seas of the early Cambrian, in creatures with simple eyes and segmented bodies, navigating a world that was just beginning to fill with predators and prey and competition for the very first time. Imagine that world for a moment. The oceans teeming with trilobites, with anomalocarids, those bizarre meter-long predators with grasping appendages and compound eyes, with worms burrowing into the seafloor, with early arthropods scuttling across reefs made not of coral, but of strange columnar organisms called archaeocyathids. And somewhere in that explosion of body plans and ecological niches, Ginsberg and Jablonka argue, the lights came on. Not human-level consciousness, not self-reflection, not language or abstract thought, just the bare minimum. A flicker of experience. Something it was like to detect light, to feel the pressure of water, to associate the shape of a predator with danger, and act accordingly. And here's what's really compelling about their argument. They don't just assert this. They try to build a principled criterion. They look at what kind of learning requires consciousness and what kind doesn't. Simple habituation, for example, where an organism stops responding to a repeated harmless stimulus, doesn't seem to require any inner experience. A sea anemone can habituate. Classical conditioning, the kind Pavlov demonstrated with his dogs, is more complex, but might still be achievable through purely mechanical neural circuits. But unlimited associative learning, where an organism can learn arbitrary new associations between compound, multimodal stimuli, can revise those associations when the world changes, can transfer what it's learned to novel situations. That, Ginsberg and Jablonka argue, requires a unified experiencing subject. It requires binding information from different senses into a single representation. It requires something like attention, something like a point of view. Now, you might be thinking, that's a bold claim. How do you get from, this creature can learn complex associations, to, this creature is conscious? And that's a fair question. What Ginsberg and Jablonka are really doing is proposing what they call an evolutionary transition marker. Not a definition of consciousness, but a reliable indicator that consciousness has emerged. The way feathers are a reliable indicator of a certain lineage, even though feathers aren't the definition of being a bird. They're saying, wherever you find unlimited associative learning in the animal kingdom, you're likely looking at a conscious creature. And when you trace that capacity back through evolutionary history, you land in the Cambrian. This is a testable claim, at least in principle. You can look at the neural architectures of different animal groups and ask which ones have the machinery to support this kind of learning. Vertebrates clearly do. Arthropods, insects, crustaceans, spiders, show surprisingly sophisticated learning abilities despite having relatively small brains. Honeybees can learn abstract concepts like same and different. Jumping spiders plan detour routes to reach prey they can no longer see. Cephalopods, as we talked about, are remarkable learners. So the capacity seems to be present across multiple independently evolved lineages, which suggests it arose early and was preserved because it was useful, because consciousness, whatever it is, gives organisms a survival advantage. But let's sit with that idea for a second. What advantage? Why would it be better to have experiences than to simply process information unconsciously? This is one of the deepest puzzles in the whole field, and honestly, nobody has a fully satisfying answer. But there are some interesting proposals. One comes from the work we've already explored, the idea that consciousness is what happens when the brain creates a unified model of the world and the organism's place in it. If you're an early Cambrian creature trying to navigate an increasingly complex environment full of predators and competitors, having a single integrated representation of your situation, combining what you see, what you feel, what you remember, might be enormously more useful than having a bunch of separate, disconnected processing streams. Consciousness, on this view, is the brain's solution to the binding problem, the challenge of pulling together information from different sources into a coherent whole that can guide flexible behavior. And this connects beautifully back to Tononi's integrated information theory, doesn't it? Remember phi, that measure of how much a system is more than the sum of its parts, how much information is integrated rather than just processed in parallel. If Tononi is right that consciousness corresponds to integrated information, then the evolution of consciousness is really the evolution of integration. As nervous systems became more interconnected, as neurons began talking to each other across longer distances and forming more complex networks, phi increased. And at some point, It crossed a threshold. The system became integrated enough that there was something it was like to be that system. Ginsberg and Jablonka's timeline aligns surprisingly well with what we know about the fossil record of nervous systems. Before the Cambrian, most animals had very simple nerve nets, diffuse networks without much centralization. But during the Cambrian explosion, we see the emergence of centralized nervous systems, of brain-like structures, of sophisticated sensory organs like the compound eyes of trilobites. The hardware was changing, and with it, perhaps, the software, the capacity for experience. Now here's where things get philosophically tricky, and I want to be honest about this. Even if we accept that consciousness evolved, even if we can point to the Cambrian as a plausible origin point, we still haven't solved the hard problem. We've just pushed it back. We can tell a story about why integrated information processing is useful, about why natural selection would favor organisms that bind sensory information into unified representations. But we still can't explain why that integration feels like something. Why isn't it all just happening in the dark, so to speak? Why does the binding of information produce experience rather than just more sophisticated information processing? David Chalmers, who posed the hard problem in the first place, has been remarkably consistent on this point. He argues that no purely functional explanation, no story about what consciousness does, no matter how detailed, can bridge the gap between mechanism and experience. You can explain every neural process, every evolutionary advantage, every computational function, and you still haven't explained why there's a subjective quality to it all. And this has led some thinkers in a direction that might surprise you. Panpsychism. The idea that consciousness isn't something that emerged at a particular point in evolutionary history, but is instead a fundamental feature of reality itself, present in some rudimentary form in all matter. Now, before you dismiss this as mystical nonsense, let me tell you who takes it seriously. Philip Goff, a philosopher at Durham University, has been one of its most articulate modern defenders. Giulio Tononi's IIT, if you follow its logic all the way down, has panpsychist implications, because phi can be non-zero even in very simple systems, which means even a thermostat, even a single logic gate, might have some infinitesimally tiny flicker of experience. Christoph Koch, Crick's collaborator, has publicly embraced this implication. And the idea has deep historical roots. It traces back through Bertrand Russell, through William James, through Spinoza, all the way to the ancient Greeks. The core intuition is this: if consciousness can't be explained by the arrangement of non-conscious parts, if you can't get experience from things that have zero experience, no matter how cleverly you combine them, then maybe experience goes all the way down. Maybe electrons don't just have charge and mass and spin. Maybe they have some unimaginably primitive form of what it's likeness. And maybe what brains do isn't create consciousness from scratch, but organize and integrate these micro-experiences into the rich, complex consciousness you're having right now. It sounds wild, I know. And there are serious objections. The biggest one is called the combination problem. If electrons have micro-experiences, how do billions of them combine into a single unified human consciousness? That seems just as mysterious as the hard problem itself. You've traded one impossible question for another. Goff and others have responses to this, but none of them are fully convincing yet. It's an open wound in the theory. But here's why I bring it up. Panpsychism represents one endpoint of a spectrum of positions on when and how consciousness arises. At one end, you have the emergentists, people who think consciousness pops into existence at a certain level of complexity, the way wetness emerges from water molecules that aren't individually wet. In the middle, you have people like Ginsberg and Jablonka, who think consciousness emerged at a specific point in biological evolution. And at the other end, you have the panpsychists, who think it was there from the beginning, woven into the fabric of the universe. Each position has its strengths and its deep, unresolved problems. And what's remarkable, what I find genuinely moving about the current state of the field, is that serious scientists and philosophers are engaging with all of these positions. This isn't a fringe debate anymore. The question of consciousness has moved from the margins of philosophy into the center of neuroscience, physics, and even artificial intelligence research. The tools we have now, brain imaging, information theory, computational modeling, psychedelic research, studies of anesthesia and sleep and disorders of consciousness, are giving us more data than we've ever had. And yet, the central mystery remains stubbornly intact. Think about what that means. We can land robots on Mars. We can sequence the human genome. We can detect gravitational waves from colliding black holes a billion light years away. But we cannot explain why you experience the color red, why pain hurts, why there is something it is like to lie here in the dark and listen to someone talk about consciousness. That gap between what we can measure and what we experience is still there, still as wide as it was when Chalmers named it in 1995, still as puzzling as it was when Descartes sat by his fire and wondered how mind and body could possibly interact. And yet there's something hopeful about where we are. Because the theories are getting more precise, more testable, more constrained by evidence. The adversarial collaborations, the no-report paradigms, the careful studies of consciousness in altered states. All of this is narrowing the space of possibilities. We may not solve the hard problem in our lifetimes, but we're learning an enormous amount about the structure of consciousness, about its neural signatures, about what it requires and what it doesn't, about where it exists in the animal kingdom and possibly beyond. And some researchers think that as we accumulate enough of these structural insights, the hard problem itself might dissolve, might turn out to have been the wrong question all along, a confusion born of how our brains model themselves rather than a genuine metaphysical chasm. That's essentially what Graziano argues, and what Dennett argued for decades before him. Maybe the mystery of consciousness isn't a mystery about the universe. Maybe it's a mystery about us, about the limits and quirks of human self-modeling. And if that's true, then understanding those limits, mapping those quirks, might be the closest thing to an answer we'll ever get. Which brings us to something I've been wanting to talk about, the practical side of all this. Because consciousness science isn't just an abstract philosophical exercise. It has real consequences for real people. And some of those consequences are already unfolding in hospitals and courtrooms and laboratories right now, in ways that touch some of the most vulnerable people on the planet. Let's start with the one that might matter most. Imagine someone you love, a parent, a sibling, a partner, suffers a devastating brain injury, a car accident, a stroke, an anoxic event where the brain is starved of oxygen for too long. They're in a hospital bed. Their eyes are closed, or maybe they open sometimes, but there's no clear sign that anyone is home. The doctors use terms like coma, vegetative state, unresponsive wakefulness syndrome. And the question that hangs over everything, the question that the family asks and the doctors struggle to answer is, are they still conscious in there? This isn't hypothetical. There are tens of thousands of people worldwide right now in states of disordered consciousness, and for decades, the only tools we had for assessing them were behavioral. Can they track an object with their eyes? Can they squeeze a hand on command? Can they respond to their name? And those tools, it turns out, are shockingly unreliable. Studies going back to the early 2000s have shown that somewhere between 15 and 40% of patients diagnosed as being in a vegetative state, meaning no consciousness, no awareness, are actually misdiagnosed. They're conscious. They can hear. They can think. They just can't move, can't speak, can't signal to the outside world that they're in there. Think about what that means. Think about lying in a bed, fully aware, hearing your family discuss whether to withdraw life support, and being unable to move a single muscle to tell them you're still here. It's one of the most terrifying scenarios imaginable, and it's not science fiction. It happens. This is where consciousness science becomes something more than philosophy. Remember Adrian Owen? He's a neuroscientist, originally from the UK, who moved to Western Ontario and did some of the most important work in this space. In 2006, Owen and his team put a patient diagnosed as vegetative into an fMRI scanner and asked her to imagine playing tennis, and her brain lit up. The supplementary motor area activated in exactly the same pattern you'd see in a healthy person imagining the same thing. They asked her to imagine walking through her house, and the parahippocampal gyrus activated. Again, just like a healthy brain. She was responding. She was in there. She just couldn't tell anyone. Owen went further. He developed a communication protocol. Imagine playing tennis for yes. Imagine walking through your house for no, and used it to ask patients simple questions. Some of them answered correctly. One patient, a man named Scott Routley, who had been diagnosed as vegetative for 12 years, was able to communicate through the scanner that he was not in pain. 12 years of assumed unconsciousness, and he was aware the whole time. Now, here's where the consciousness theories we've been talking about all night become directly relevant. Remember Massimini's zap and zip technique from earlier? The one where you send a magnetic pulse into the brain and measure the complexity of the echo? That technique, transcranial magnetic stimulation combined with EEG or TMS-EEG, has turned out to be one of the most promising tools for detecting consciousness at the bedside. Massimini and his colleagues developed something called the Perturbational Complexity Index, or PCI. You zap the brain, you record the response, and you calculate a number that reflects how complex and integrated that response is. And what they found is remarkable. In healthy awake people, PCI is high. In deep dreamless sleep, it drops. In REM sleep, when you're dreaming and presumably conscious, it goes back up. In people under general anesthesia, it drops. And the cutoff is surprisingly clean. Above a certain threshold, the person is virtually always conscious. Below it, they're virtually never conscious. When they applied this to patients with disorders of consciousness, they found exactly what you'd hope and fear. Some patients who looked vegetative had PCI values above the consciousness threshold. They were conscious. The tool was detecting what the behavioral assessments had missed. This is Tononi's integrated information theory, making a real clinical difference. The whole idea behind IIT, that consciousness corresponds to integrated information, that the complexity and interconnectedness of neural activity is what matters, that theoretical framework is what motivated the development of PCI. The theory predicted that consciousness should correlate with a specific kind of complexity, and the clinical tool built on that prediction actually works. It's one of the clearest examples in all of science of a philosophical theory about consciousness leading to a practical medical instrument. And it's not just about diagnosis. It's about prognosis, too. There's growing evidence that patients who show higher PCI values, even when behaviorally unresponsive, are more likely to recover. That information changes treatment decisions. It changes whether families maintain hope. It changes everything. But here's the thing, and this is where the ethical complexity really deepens. What do you do with the patients who score below the threshold? Does a low PCI mean they're definitely not conscious? Or does it just mean their consciousness is organized in a way our current tools can't detect? This is where the limits of our theories become the limits of our moral confidence. If IIT is wrong or incomplete, then PCI might be missing forms of consciousness that don't look like integrated information in the way the theory predicts. If global workspace theory is more correct, maybe we should be looking for different signatures entirely. The theoretical uncertainty translates directly into clinical uncertainty. And clinical uncertainty, when you're talking about life and death decisions, is agonizing. So that's one practical domain: clinical neurology, disorders of consciousness, the question of who's aware and who isn't. Let's talk about another one that's becoming more urgent by the year, and that's artificial intelligence. We touched on this earlier when we talked about Blake Lemoine and LaMDA and about the Chinese room argument and its limitations. But the practical question is getting harder to avoid. As AI systems become more sophisticated, as they generate more convincing language, as they're embedded in more aspects of daily life, the question of whether any of them are conscious or could become conscious stops being a thought experiment and starts being a policy question. Here's why it matters practically. If an AI system were conscious, it could suffer. And if it could suffer, we'd have moral obligations toward it. We couldn't just shut it down when it became inconvenient. We couldn't run millions of copies and delete them. We couldn't subject it to endless loops of testing without considering its welfare. The moral implications are staggering, and we currently have no reliable way to assess machine consciousness. This is exactly the problem that a group of researchers tried to address in a 2023 report. Robert Long, Patrick Butlin, and several others, including some of the theorists we've spent the night with, like Lau and Seth and Tononi. They published a white paper asking, given our best current theories of consciousness, what would we look for in an AI system to determine whether it might be conscious? And their approach was clever. They didn't commit to any single theory. Instead, they drew on multiple theories: IIT, Global Workspace Theory, Higher Order Theory, Attention Schema Theory, Predictive Processing, and extracted indicator properties from each one. Things like, does the system have a global workspace where information is broadcast? Does it have recurrent processing? Does it model its own attention? Does it have something analogous to embodiment, to sensory feedback loops? Their conclusion was measured but important. Current AI systems, including large language models, probably lack most of the indicators. But future systems, especially ones with different architectures, systems with more recurrent processing, with embodied sensory loops, with self-modeling components, might satisfy more of them. And the uncomfortable truth is that we might create such systems before we've settled the theoretical questions that would let us know whether they're conscious. We might build minds before we understand minds. And this connects back to something Graziano's attention schema theory suggests, that what we call consciousness might be a specific kind of self-model, a brain's simplified representation of its own attentional processes. If that's right, then it's at least conceivable that you could build a machine that constructs a similar self-model. And if you did, would it be conscious? Or would it just be modeling consciousness without having it? This is the hard problem all over again, but now with engineering stakes. There's another practical frontier worth mentioning, and it's one that loops back to something we explored earlier: psychedelics. The research we talked about, the rebus model, the entropy increases, the DMN dissolution, all of that is now feeding into clinical trials for treatment-resistant depression, PTSD, addiction, end-of-life anxiety, and the results are genuinely striking. Psilocybin-assisted therapy, in particular, has shown remarkable efficacy in several trials. The FDA granted it breakthrough therapy designation for depression, and what's fascinating from a consciousness science perspective is that the therapeutic effects seem to be closely tied to the quality of the conscious experience during the session. Patients who report more profound alterations of consciousness, more ego dissolution, more mystical type experiences, tend to show greater therapeutic benefit. The consciousness itself seems to be doing the therapeutic work. This means that understanding consciousness isn't just abstractly important for treating mental illness, it's mechanistically important. If you can understand why certain alterations of consciousness are healing, you can potentially optimize treatments, develop better protocols, maybe even design drugs that target specific aspects of conscious experience more precisely. Robin Carhart Harris and his group at UCSF are working on exactly this kind of translational research, trying to bridge the gap between the neuroscience of consciousness and clinical psychiatry. So you see how all of this comes together. The ancient question, what is it like to be aware? What is this inner light of experience? Turns out to be connected to some of the most pressing practical questions of our time. How do we care for brain-injured patients? How do we navigate the rise of artificial intelligence? How do we treat mental illness? How do we think about animal welfare, given what we now know about the distribution of consciousness across the animal kingdom? Remember that Cambridge Declaration, the one signed in 2012, saying that many non-human animals possess the neurological substrates of consciousness? That declaration has influenced animal welfare legislation in several countries. Consciousness science is literally changing laws. And yet the deepest question remains open. What is experience? Why does it exist at all? Why isn't the universe just a vast collection of processes happening in the dark, with no one home to witness any of it? We've spent this whole night circling that question, approaching it from different angles, from Descartes' fireplace to Chalmers' zombies, from Tononi's phi to Seth's controlled hallucinations, from the Cambrian explosion to the combination problem, from sleeping brains to psychedelic brains, to brains that might not be brains at all. And I don't have an answer for you. Nobody does. Not yet. Maybe not ever. But here's what I find genuinely comforting about that, and I mean this. The not knowing isn't a failure. It's an honest acknowledgement of where we are in a very young science. Consciousness research as a rigorous empirical discipline is really only about 30 years old, dating back to Crick and Koch's 1990 paper and Chalmers' 1994 formulation. 30 years. That's nothing. 30 years after Newton published the Principia, people were still arguing about whether gravity was a real force or some kind of occult nonsense. 30 years after Darwin published On the Origin of Species, the mechanism of heredity was still completely unknown. Mendel's work had been published and ignored, and DNA was decades away. Sciences take time. The big questions take the most time. And in the meantime, we live inside the mystery. Every moment of your experience, right now, the sound of these words, the feeling of your body against the bed, the soft weight of the blankets, whatever half-formed thoughts are drifting through your mind. All of it is consciousness doing its thing. You are the phenomenon. You don't need to understand it to be it. You're already the most sophisticated example of it that we know of in the entire universe. A human mind, awake or drifting toward sleep, reflecting on its own nature, wondering about itself. That's kind of extraordinary when you think about it. Out of all the matter in the cosmos, all the hydrogen clouds and dead rocks and empty space, some of it, right here, arranged in this particular way, in this particular body, is having an experience, is wondering, is listening, is slowly, gently letting go of the day. So let that be enough for tonight. You don't need to solve the hard problem before you fall asleep. The theories will still be there tomorrow. Global Workspace and IIT and predictive processing and all the rest, still competing, still being tested, still being refined. The researchers will still be at it. Tononi in Wisconsin, Seth in Sussex, Dehaene in Paris, Lau now at Riken in Japan, pushing the boundaries of what we can measure and what we can understand. The mystery will keep. It's patient. It's been waiting since the first nervous system flickered to life in some ancient ocean, and it'll wait a little longer. For now, just notice what it's like to be here. The warmth, the quiet, the way your breathing has probably slowed without you deciding to slow it. That's your brain doing its thing, regulating, predicting, modeling, all without asking your permission. And somewhere in all that machinery, somehow, there's you. There's this. There's the soft, irreducible fact of what it feels like to exist. That's the deepest mystery there is. And you're soaking in it. So rest now. Let the questions dissolve into the dark, the way dreams dissolve into morning. You've traveled a long way tonight. From ancient Greece to modern neuroscience. From philosophical zombies to octopus minds, from the firing of a single neuron to the integrated complexity of a dreaming brain. That's more than enough for one evening. The rest can wait. Everything can wait. Just this. Just here. Just the quiet hum of being conscious. For as long as it lasts, which tonight means exactly as long as it takes for sleep to find you and carry you gently, gently into the dark.